In this video, we're going to look at the relationship between temperature and reaction rate. And so we talked a little bit about this rate law K, which is a constant that is unique for every reaction. And the only thing that can change K is temperature. Concentrations don't change K, only temperature. And the Arrhenius equation shows us how temperature affects K, because K is equal to A, which is frequency factor, which is something we'll talk about in a little bit, multiplied by exponent, so E raised to the power of negative EA, which is activation energy, which is the energy you need to put into the reaction to make the reaction happen, divided by RT. R is the gas constant and T is the temperature in Kelvin. All right, so let's take a look at this activation energy a little more. So the plot you're looking at is energy on the y-axis and reaction progress on the x-axis. Remember, negative energy is good, positive energy is bad. So what's happening here is that we have two hydrogens plus an oxygen makes H2O. So here's our two hydrogens and here's our oxygen. And when they start to react, they'll create what is known as the activated complex or the intermediate state. And this is a very high energy state, very unfavorable state to be in, because you haven't made water yet, but you're breaking the bonds between oxygen, you're breaking the bonds between hydrogen, and you're beginning to form the bonds between hydrogen and oxygen now. And you need to put in energy for that to happen. That's the activation energy. So to make water, we have to get over this hump, and we have to put energy into that hump to get over that hump. It's kind of like running up a hill, right? So to get up that hill, you have to put in energy through your legs to get up that hill. And once you're over this hill, it's all downwards. It's easy to go downhill. So once you get to this very top of the activation state, the activation energy, you're going to go down and make your products. And in this reaction, it is an exothermic reaction. The products are lower energy than the reactants. Since energy can never be created or destroyed, that energy was released out into the universe. So we're going to look at this idea of activation energy and a reaction in general for this specific reaction, where we have a methyl and a nitrogen simply switching places in our molecule. And to do this, you have to break the bond between this carbon and this nitrogen while forming a new bond between these two carbons. And so this is what the plot looks like, the energy plot looks like for that, where we start our reactants, and at our transition state or activated complex, our nitrogen has broken from the carbon, and our carbon is beginning to form that new covalent bond. And to make that happen, we have to put in energy, which is our activation energy. Then our new product is lower in energy than our reactant, and the energy difference between our reactant and our product, that's the change in enthalpy, or delta H, for our reaction. Again, our products are lower in energy than our reactants, so this is an exothermic reaction. Right? So activation energy is difference between the top of this hill and the reactant. And we also have frequency. The idea of frequency is how many molecules will make it up this hump in a given time period, right? And that's what we call the frequency factor. It's every time we make an attempt to go up that hill, we add another count to our frequency. And for this reaction, this reaction starts with this N moving upward. So that every time that happens in our molecule, that is added to our frequency. How many times this reaction attempts to happen over a given period of time. And if we look at the Arrhenius equation, our exponent, E raised to the power of negative activation energy divided by RT, has to be between 0 and 1. And that's because this is our frequency factor. This is telling us from 0% to 100% how many molecules will make it over that energy barrier. So if activation energy is 0, then 0 raised to the power of anything is 1. So 100% of our molecules will go towards the reaction. The higher the value of this activation energy, the closer this value is to 0, this exponent, so fewer molecules will make it across. And by increasing temperature, what you're doing is you're increasing this frequency factor. By increasing temperature, you're making this exponent go closer to 0. And remember, the closer to 0 it gets, the closer that number is to 1, which represents 100% of our molecules making it over that activation barrier. And here is just the idea graphically. We have two temperatures. T1 is cooler than T2. And we have the fraction of molecules that have enough energy to go over the activation barrier. Again, remember, with temperature, molecules have kinetic energy. The more temperature they have, the hotter they are, the more kinetic energy they'll have. And so on average, you will have more molecules that can get over that activation barrier than you do at the lower temperature. And we can graph this. We can show the Arrhenius equation graphically, and that's by putting it in the line equation. So to graph the Arrhenius equation, you do natural log of K, which is your rate constant, that's going to be your Y, equals minus activation energy divided by R, that's your slope, multiplied by 1 over temperature, that's your x-axis, plus natural log of A, which is that frequency factor, that would be our y-intercept. And we can also use the Arrhenius equation if we only have 2 data points. So let's say that you want to figure out what the rate of your reaction is going to be at a second temperature. Well, all you need is that second temperature. You need your rate constant at that first temperature. You need the temperature of that first rate constant. And you just need your activation barrier. And you can figure out the rate constant of your second temperature. So by just doing two data points, we can use the Arrhenius equation as well. That's it for this video. See you in the next one.